Okay, so here's what we were talking about last time, higher order partials. You remember partial derivatives. They're a lot like single variable derivatives, and so not surprisingly, because you can take higher order derivatives with single variable derivatives, likewise you can take higher order partials. And we talked through the algebra last time. We made this last observation that, this occurrence that happened here, that the mixed partials, you got the same answer no matter which order you did the partials in. Not a coincidence. This is, I want to say, usually true in sort of everyday experience. So the condition is you need for all second order partials to be continuous. So again, this is true in a lot of situations. I mean, let's suppose the functions you're looking at are polynomials. All of the partials are going to be polynomials, and all polynomials are continuous, and therefore, so even before you start taking derivatives, that's going to be true. Right. Likewise with trig functions where they're defined and that kind of thing. Okay. So now what I want to do is ask, what do these second partials look like? All right. So we have an answer to this question in single variable calculus. It refers to concavity. Right. There's a little argument you go through about how the derivatives on a graph. By the way, this is in the graph context. In the graph context, very importantly. Concavity, so the derivatives refer to slope, and if you think about how slopes change as you move along, that gives you concavity. Right? This is a geometric argument from Calc 1. And the same thing works for these first, the non-mixed second partials. Let's walk through an example. What does fxx mean? Well, first, because we're starting by taking an x partial, we're going to fix x. That was supposed to be a straight. Let me do a better job than that. We're going to fix x. That means we're taking this cross-section, vertical cross-section, parallel to the x-axis. Sorry. I was fixing y. Sorry. Fix x. Right, we're fixing x because that's the value of x that we're fixing. Pay attention. And having fixed x, we're, get a curve, slope of the tangent line and all that. And this first derivative is that slope. Right? So then, what about the second? What happens when you take a second partial with respect to x? Well, again, fix x. Okay, I don't need to. I already did. I'm already in this cross-section plane, so that second fixed x, whatever. And then I just look at how those slopes change. And you get this familiar idea of concave up. I'm sorry. Apparently I'm in some sort of a haze from being in a hurry to get here and get done on time, and I did this whole thing backwards. I had it right the first time. Let me start over. Okay. Slowly and carefully. We're not fixing x, we're fixing y. Partial derivative with respect to x means x is the variable, so we are fixing y, and as I had it drawn in the first place. That's our cross-section plane. Alright, is everybody good? By the way, if you ever see me blow it like that, you're very welcome to raise your hand and say, isn't it the other way? I know y'all are you're seeing these ideas for the first time, so maybe you weren't confident. Maybe you thought you were the one that was confused. But it was me. So anyway, sorry about that. Okay, same argument in this plane. Partial with respect to x says slope of those tangent lines. Next partial says how do those tangent lines change as you move along and you get concavity. So here, concave down, and so the second derivative is negative. Everybody happy? Did I recover from saying it backwards? Everybody good? Okay. All right. Okay, likewise for the y partial. I'm going to let y'all do this one yourself, but if you want to know the partial with respect to y, then you'd fix x. In other words, look at a cross-section in the y direction. And same argument, how do those slopes change, and you get positive in this case. All right, so think through the details. where it gets a little confusing is, what if you have mixed partials? So what if we take the x partial of the y partial of f? Now here we don't get the advantage of just being able to say like we did previously, it's all in one cross-section. Because it isn't. This is very weird, but when we're looking at these y partials to start with, we're looking at planes where x is fixed. We're looking at cross-sections that are perpendicular to the x-axis. And I want to know how those cross-sections change as I move in the direction of the x-axis. In other words, then I'm going to be fixing y, and x becomes not fixed like it was here, but now it's a variable. So at different stages in the process, these variables are playing different roles. So what we're about to explore here, there is no version of this in single variable calculus. And so don't think, oh yeah, it's just like the... Nope. There is no single variable version of this. Okay. All right. So to make sense out of it, I want to make a particular choice in how to interpret these specific partial derivatives for maximum interpretation convenience in this situation. I want to view the initial y partials as big slopes. And I want to view these x partials in this other way. Remember, we had this other point of view on what a partial derivative is. And it says, yeah, how fast is this, whatever you're taking a partial of, how fast is that changing while you're moving in the x direction? All right, so two different interpretations for the two different partial derivatives we're looking at. All right, and now let's actually do it. Now, by the way, I didn't draw the surface here. The surface would have been hard to draw, and I don't want to make the picture uglier. So I'm just going to draw some samples of what these, various cross-section tangent lines would look like, and then you can kind of piece together in your mind what kind of a surface would make this happen. But so here's a point. Let's talk about partials and with respect to y. Partials with respect to y say look in the y direction. Right. So at this point here, for example, there's the point above it on the graph. If I had drawn the graph. And there'd be some tangent line in the cross section, for example, maybe for example, it might look like that. And that slope of that line is the y partial at that point. And then you can imagine doing the same thing at different points. Like maybe you ought to know, let's say here, at that point. Going in the y direction. Maybe that, sitting up above there. At that point, maybe that's what the cross-section would look like. And so you get various different cross-sections with different slopes as you move in the y direction, but from different points. Yeah. Okay, so that's just some examples of some y partial derivatives. Now notice, those are the things, those y partials, those slopes, are what I want to know, how fast do they move, how fast do they change when I move in the x direction. So I'm going to look at these green slopes, and I want to know as I move in the x direction, how are they changing? And you'll notice that the little sample green lines that I drew, I've drawn them as actually changing. So as I move in this x direction, as I come out of the page, the slopes, kind of in the back, the slopes were like this. And then as I come out of the page, the slopes are tilting upward. Right? So now you got to kind of use your imagination. You can do this with your hands if you'd like. But think about what kind of a shape does my forearm here sort of trace out, right? So it's, and I claim it makes a kind of a twisted. Let's see here. It makes imagine I'm holding a sheet of rubber by the four corners here. It's like I'm twisting that sheet of rubber. So this is the geometric interpretation. It's very hard to draw a halfway decent picture of, as you can see here. But this mixed partial, the x partial of the y partial, is measuring how much of a twist, how much of a sort of, they call it torsion, but how much of that twisting of the surface is going on? Yep.
Clarify.
Yeah.
Is x the first partial?
No, so the y is the first one. So here's the function, and we are first taking a partial derivative with respect to y, and it is that y, the y partial that I've already taken, that I'm taking the x partial of. Yeah, so operators always act by whichever one is closest. Yeah, and I admit that typically we go left to right. That's probably what you were thinking, right? But it's more like with nested parentheses. So the y is closer. The y partial is closer. Yeah. Right. Okay. All right. So this is a good picture to just kind of you gotta kind of stare at it and think it through, and it's a good one to digest. Okay. Okay. Yeah. Oh yeah. Mm-hmm. Yeah. Please.
I was wondering why it still works then if you reverse the order in which you take the fractionals.
Yeah, and that's hard to get a good geometric intuition of, except for as follows. This is going to be a literally hand-wavy appeal, okay? But again, imagine a sheet of rubber. I would do it with paper, but paper is physically incapable of twisting and bending the way I need it to do, right? So I don't know where to get a sheet of rubber. Okay, but imagine a sheet of rubber, and imagine that I'm holding on to it by all four of its corners. And now imagine that I twist it like this. Right? Now, if you look at what my fingers are doing, right? My left hand, the one is going up, the one is going down. My right hand, it's the other way. Well, now, okay, but instead of thinking about how these are working in conjunction with each other, you could think about how these are working in conjunction with. When I do this, it's almost like I was doing that. See? Okay, so, see this?
Okay.
Right? Now, ignore my thumbs. Look just at these fingers. Right? So just these fingers here. It's like there's a twist going in the other direction. Right? So this twist is really the same as that twist. So it's not the craziest thing in the world. Now that's, again, literally hand wavy. Right? But I think there's a pretty reasonable geometric satisfaction to be had. It's a good plausibility argument, but the proof is beyond what we can reasonably do in this course. Yeah. Okay. All right, so I want to say one last thing about partial derivatives, and that is that while, now let me remind you, I don't think partial derivatives should be your foundational default, fundamental way of thinking about derivatives of multivariable functions. There's a better one that's going to come along Friday, I think it'll be, that in my mind is more sort of fundamental. And we're going to see one today that's it. Anyway, okay. But so partial derivatives, again, don't overinterpret and don't overbuy into the importance of partial derivatives. That said, they are very important, and people use them all the time because they're so easy to compute, right? And so if there's an object, if there's a differential object of some sort that you're interested in talking about for some reason, if you can express it in terms of partial derivatives, then anyone who works with it will thank you, because you take something like Laplace's operator here. And there's different ways to write that. It's got interpretations in physics that in physics and engineering classes you'll learn about why we care about that. It has to do with understanding how electric potential behaves. But here it's written in terms of partial derivatives, which means that if I ever want to compute Laplace's operator, no problem. Crank, 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 crank. It's super easy to compute because partial derivatives are so easy to compute. Right, so lots of equations that you're going to see in physics classes and engineering classes are written in terms of partial derivatives. So the heat equation. This describes how heat moves around. Right, if you have a hot object and you put it into contact with a large object, and you know that the heat from this hot object is going to kind of flow. I mean, eventually all that heat's going to get in through the whole large thing, but it's not just going to immediately transfer exactly instantaneously. Right? And after it's been sitting there for just a few moments, this side's going to be hot and that side's still cold. So how does the heat flow through there? Well, this is the equation that describes that in 2 dimensions. And you notice partial derivatives all over the place. Likewise, how waves move. Here's what's called Schrodinger's equation, which is in quantum mechanics a theory about the nature of matter. Right? It's all partial derivatives. So, by the way, this I should have mentioned. This symbol here is a shorthand for the Laplacian. So, anyway, all partial derivatives. Okay. All right, next topic, increments and differentials. So this is kind of a weird section. There's a couple of things that have to get said, observations that have to get made. Y'all remember we did talk about linear approximations last time, I guess it was. Right? Well, I just want to point out that there is some related language, and hopefully none of this is really news. But let's go back to single variable calculus, and I'm going to draw a familiar picture that y'all will recognize, I'm sure, and that is, if you have some point x there, and if we have some curve, there's a curve, and then we can talk about the linear approximation, the tangent line. Right, the graph of the linear approximation is the tangent line, and then you can talk about moving over by some amount delta x. So here's x plus delta x. And you can draw this. And note that there's two values of relevance. Right? There's the actual value of the function there, which is f of x. And then there's our linear approximation of that value, L of x. Right, so L of x and f of x are not the same thing. The whole idea of L is it's a linear approximation. Approximation means it's probably not right. It means it's going to be wrong at least a little bit, so these are going to be different values. Okay, so the two bits of lingo that we need to talk about are, I'm going to talk about this thing called the increment. The increment said, how much did the function actually change? The increment is that distance there. The actual change in the function from x to x plus delta x. And then there's this other thing, the differential. The differential says, in an ideal world where we just magically know how to compute every function in sight, then we can talk about that increment. But in the real world, I know how to take derivatives, but derivatives are a tool for understanding these increments. They're an easier thing to compute. The linear approximation of how much the function changed. So the increment and the differential, not the same thing. I hope these are familiar ideas, that you remember these from single variable calculus class. So one way to say it is differentials are a way of approximating increments. Differentials are a way of approximating how much a function's actually changed. Just an approximation. Okay, so same deal for multivariable functions. We can talk about a differential. Different formula for linear approximations. Let's see here. Here's our formula for linear approximations. Old news. We did this last time. All right, so there's two different terms here. You have to have both of these terms so that the partial derivative will work out the way they're supposed to. And notice that in the analogy, the approximated new value and the old value, right, both appear there, and so I can look at the difference. And the difference, the df, is just kind of what's left over there. Right, so by the way, what a lot of students get stuck on is, this is F and this is L. But of course, these are at the base point. This is at the point, here I'm calling it A. But this is at the point where you're doing your approximation, and of course, at the point where you're doing the approximation, L and F have the same value. Okay, so this is just a multivariable version of a differential. In the single variable version, it's just df is equal to the derivative times dx. Here, there's two terms. They're both a derivative times a change. It's just that, well, there's the x partial times the change in x. And there's also the y partial times the change in y. It's analogous except twice in two different directions. Okay. All right. So this is the formula for the differential. If you look at this formula, you notice something kind of interesting about it, by the way. Notice that there are two partial derivatives. There are two, changes in the inputs, one for each variable. And notice the form of the construction here. We have this times that plus that times that. It looks like a dot product. And in fact, it is a dot product. It's a dot product of this green vector with this purple vector. And when you look at it that way, and then you realize, well, x minus a comma y minus b, that's just the difference between the x vector. Whoops, I wanted to change colors. The x vector and your original starting point a vector. That's literally x minus a vectors. And what we have is we have that the change in the output, our differential, our estimate of the change in the output, is very closely related to the change in the input. We have a vector change in the input that's strongly related by this formula to the differential change of the output. And because this is such a, input changes, output changes, it's such a close connection between things that we're naturally interested in, this vector here that does that deserves a name and a notation. So we call this the gradient vector of the function f at the point A. So right now, I want you to think of this purely in an algebraic way. Yes, it turns out that a wonderful, I'm going to say coincidence, there is a geometric interpretation of the gradient as well. I'm not going to talk about that right now. We'll get to it later. But right now, it's an algebraic shorthand for these partial derivatives. Yes?
Is the upside down triangle a nabla?
Is what now?
A nabla?
It is a nabla. Now, do you know what? Have you seen nablas elsewhere?
No, I just need to know the name.
Oh, yeah. It's nabla, and I remember being told at one point that has some. That it exists outside of the context of math, but I don't remember. Does anyone know where nabla comes from? Okay, all right, don't worry about it. By the way, the common math lingo for this symbol here is del. So people will say del f. Or, probably in this context, even more common is to say gradient of f. But yeah, but nabla is some other context. It's the word. Yeah. Okay, so here's saying it over again, having rewritten x minus a as dx, which I think is a natural shorthand because it's the change in the input. We were at the point A, now we've moved over to the point S. My position has changed. Position being represented by the x vector. This says change in x. Okay, so I'd like to point out now that the gradient is playing a role here, much like the single variable derivative. Let me remind you of an old formula from way back when. df is equal to df dx times dx. Y'all remember this? Right? It's a temptation to say, well, the dx is canceled, so of course it's but anyway, this is a statement about what derivatives do. Derivatives, you can think of derivatives as fractions. I want to try to, again, encourage y'all away from thinking of derivatives as fractions, and now instead think of derivatives more as factors. Derivative is something you multiply by the input change to get the output change. Right? And again, this is an old single variable concept. And notice here that the, the derivative and the gradient are playing analogous roles. In both cases, single variable derivative, gradient, These are the things that you multiply by input changes to get output changes. Now, to be fair, it's a dot product in this case. Okay, it's a little different. Well, it's a different world. In multivariable context, of course, things are going to be a little different, but very analogous. Note also, broad stroke. We made this statement that in general, one common thing that we're going to notice about all the various different kind of derivatives we're going to create in this class is that the relationships between input changes and output changes. Well, that's exactly what this is. It's a connection between input changes dx and output changes df. So a lot of people would look at this and say, oh, wow. I mean, this is all-encompassing. There is no, asterisk. This only works if you hold all the variables constant in a super unnatural way and only allow one single variable at a time to change. There is no such asterisk. This says, oh, did you change your inputs? Oh, okay. Dot with the gradient vector. Bam, there's your linear approximation for your output change. Very compelling case could be made that this is more fundamentally a derivative than partial derivatives. Everybody see what I'm saying there? It's a neat observation. So again, so please don't just the partial derivative was the first derivative I saw, and so that must be fundamentally what derivatives are. I don't think that's right. I think this is a better candidate, and then I'm going to also show you a different sort of point of view on these things a little while later. That's another pretty strong candidate. Okay, all right. So by the way, this generalizes. We saw, what happens to these linear approximation formulas when you have more than two input variables? Well, you get more terms. When you have more terms, you would just have, instead of a dot product of a vector with another vector, each of which has two variables, well, more terms would just mean that you just have more coordinates in those vectors, and they just become vectors in higher dimensional domains. Yeah. Okay, so same story in different dimensions. Okay, let's see an example. By the way, how did we use linear approximation formulas back in single variable calculus? How did we use, differentials? Well, one thing was to do that we did was, suppose you want to compute that. It's hard, right? I don't know how to evaluate this function, but one thing you could do instead is say, well, I'm not going to compute that. I'm going to compute this. And the way I'm going to compute that is I'm going to take the value that I know and I'm going to add the differential that comes from knowing the derivative. Okay? And so y'all have seen examples of this kind of thing. Here, I'm going to show you now a multivariable version of that. Suppose you want to compute that weirdo expression right there. And it's hard for a lot of reasons. For one thing, it'd be slightly inconvenient to compute 3.02 squared. It'd be a little annoying, not that bad. But by hand, anyway, we don't know how to compute e to the power of 0.01. And I know I hear you thinking, well, yeah, just pull out your calculator. Okay, how does your calculator do it? Your calculator does it by a more sophisticated means than what I'm talking about. From first principles, in using, wanting to develop the ideas, not just capitalize on ideas other people have already had. This is hard, computing e to the power of 0.01. And then once I have hypothetically done that, taking cube roots is hard, right? Okay. So the observation I want to make is that what we're interested in, that is the value of a multivariable function. That's the value x. This is the value y, and we're looking to evaluate this function, cube root of x squared minus e to the y. So you notice the structure of the expression you're interested in, and the annoying numbers that you're looking at to give them names, and now you've got a multivariable function. Okay, so we're interested in computing that at the point when x. Where am I going? Where x is 3.02 and y is 0.01. Okay, now one way I can think of that point is I can think of it as, look, it's near this base point. It's near 3, 0. It's not exactly 3, 0, but it's pretty close to 3, 0. And that's, I would get to it from 3, 0 by moving a differential amount 0.02, 0.01. Right? If I think of this as a starting point, this is how I could change in the domain. If I take this starting point and add this differential input, then I get 3.02, 0.01. So what I'm going to do then is, with this setup in mind, I'm going to compute my differential as gradient.dx. Oh, there's supposed to be I got a typo here. That's dx vector. Sorry about that. Right, make sure to change that on your copy of the notes if you have a printed copy of the notes. Sorry about that. And everything in sight is just a matter of computing. And, of course, I've arranged this example to be computationally convenient. So the gradient is just made up of a bunch of partial derivatives, and partial derivatives are easy to compute. Again, I wanted a highlighter. Sorry. Partial derivatives are easy to compute. I'll let you guys take those partials. Make sure you can do that. Okay. The differential, we just agreed, was that. And so, of course, the gradient you have to evaluate at the point in question. You have to evaluate it at x equals 3, y equals 0. And a little bit of arithmetic. And this gradient at that point ends up being that. We agreed already that the differential input is that. It's an easy dot product. And you end up with your differential, that dot product being that. Approximately, I had to round off because there's a repeating 6 here, so I just rounded it off to this because we're just approximating. Okay. So that's your differential. Now, of course, very importantly, this is not the value of the function. This is not our approximation of the value of the function. This is our approximation of how much the function has changed. Right? So that, you notice, is what you have to add to f of a to get f of x. F of a is easy to compute. That's just 2. And so you end up with, as your approximation of f of x, approximately 2.009167. And look at the correct value. Again, this is an approximation with infinite expansion, right? But 2.009154. So really close, right? By using the multivariable differential. Everybody happy? Okay. All right. Okay, so the next thing I need to talk about in this section is I need to give you a rough idea of something I'm not going to be able to define precisely, because a truly satisfying discussion of differentiability, which is going to be my goal for this page of notes, a truly satisfying discussion of that is long. We don't have time. I could easily spend a lecture. I could actually pretty easily fill 2 lectures on what is multivariable differentiability. It's hard, it's complicated, lots of weird sort of counterexample. There's lots of weird things that can happen in the world of attempting to define multivariable differentiability for which there are no single variable analogs. So it's a fascinating conversation that we don't have time for in Math 212. So here's what you do need to know for sure. You need to know what it means for a function to be continuously differentiable. And the good news is that it means exactly what you would hope. The single variable notion of continuous differentiability, well, it's got to be differentiable, so the derivatives have to exist, and those derivatives have to be continuous. It's exactly the same thing in multivariable. I need for the partial derivatives to exist, and I need for them to be continuous. So nothing that different here. Okay. Here's another true fact that should look familiar. If a function is continuously differentiable, then that means it must also be differentiable. Also true in single variable calculus. It's sort of tautological in single variable calculus. I mean, it's part of the definition in single variable calculus. But nevertheless, it's a true fact in single variable calculus, and good news, it's still a true fact in the multivariable context. What is hard to talk about is what this actually means. What does differentiable mean in a multivariable context? So I am going to talk about this a little bit. It turns out that differentiability is important, but here's how y'all are going to use differentiability most of the time. Most of the time, you're going to take a function, you're going to compute the partial derivatives, confirm that they exist, note that they're continuous, and then cite this result that says, therefore the function is differentiable. And therefore any theorem that requires my function to be differentiable, cool. I can go with it because I know even more about my function. I know that it is continuously differentiable. Okay. All right. That being said, now here comes the nebulous part. What is the precise definition of differentiability? I'm not going to answer that question exactly. I am going to show you approximately what it means. Loosely, from an algebraic point of view, it means that the differentials give good approximations. We just talked about differentials. We have a formula for computing differentials. And good approximations, I put this in quotes. What is good? What is a good approximation? Right? It's hard. If you're approximating a really, really, really small number, and your approximation is also a really, really, really small number, that means they're really, really close to each other. Does that mean it's a good approximation? It's not. It could be 5 times the other really, really, really small number, and yet they're still very close to each other. So, what a good approximation is a little bit harder to define. But anyway, roughly speaking, from an algebraic point of view, that's what differentiable means. The approximations are good. Geometrically, it means that if you're looking at the graph, again, graph, got to be graph. Then the tangent plane is what I'm going to call a good tangent plane. And what does that mean? What is the difference between a good tangent plane and a not so good? What's the alternatives? What could possibly go wrong? And again, that's a long rabbit hole that we can't go down. So think of these as bits of good news. If you know a function is differentiable, then that means that your differential is good. Is it going to be a good approximation? It means that there is a tangent plane that is geometrically exactly what you would think it is. So it's all shaping up to be good stuff. The way we write this down, though, is that a function is differentiable if there exists some vector that makes this multivariable limit equal to 0. Now, if there is such a vector, hopefully it's no surprise that that vector is the gradient of f. Yeah, question. Yeah.
What is that symbol after vector c?
Yeah. So both of these little symbols here, little mathematical shorthand. The backwards capital E says there exists, and the backwards kind of E-looking little round thing says such that. Yeah, it's just mathematician shorthand. You'll probably see me doing that a lot. Good thing to make a note of. So I claim that, look, if this vector exists that makes this equation work, then in fact that vector is the gradient vector, and I persuade you, a plausibility argument for that is, notice that is the increment, and that is the differential, if C is the gradient vector. So what this is saying, I mean, you can kind of see it happening, is that, we're looking at the increment, the actual increment that we're truly interested in, the differentiable that, disappointingly is all we're able to actually compute, and we're hoping that our approximation and the real value are not that far from each other. That's what it means to be a good approximation, and that the difference is small. Right, so this numerator is really easy to motivate. Now, why you have to divide by the magnitude of h is a longer discussion, and that's, rabbit hole. I don't want to go down there right now. But that's anyways, part of the intuition for this expression. Okay. Okay. So again, in Math 212, we just don't have time to talk about that in any more detail. So here's what's again the important things you need to know. You need to know what continuously differentiable means. You need to know that continuously differentiable implies differentiable. And you need to know that differentiable means good things. All right, everybody good? Okay. And this is worth noting. Why do we care about differentiability? Why don't we just go through our life just dealing with continuous differentiability? And the answer is that's too constraining. There are theorems, true, important theorems that are good to be able to work with as broadly as possible that do not require continuous differentiability. They only require differentiability. So if you were to require continuous differentiability, the results would still be true, but you'd be tying your hands unnecessarily. So the sort of the sharp condition for these many theorems that makes them work is this elusively defined differentiability. So that's why you need to know that it very importantly is not the same thing as continuous differentiability. Okay, moving along. Need to get some headway into the chain rule. By the way, here's our old, if you have a function from R2 to R1, variables named like that, here's our formula for differentials. Old news. Different notation, using Z for the output instead of F. But old news. Right, you can see the gradient vector in here that you're dotting with the input differential to get the output differential. So, just like we were talking about. Note that that's a reference to what's going on with this function here that I've drawn a picture of. You can see, R2 to R1, R2, variables x and y, output R1, variable z. In the domain, in R2, you can see we have these differentials dx and dy, and we're computing dz there in the target. So blue is in the target, purple's in the domain, right? And the function here, the function has these partial derivatives, right? So the green is allowing you to take the purple input changes and deduce the blue output change. Okay. All right. So notice that is looking again only at this part of the picture, and so the idea here, what I want to introduce to see what happens when I do this. What happens when I say let's view x and y as functions of t, like this now. So now notice we have a composition of functions. Yeah, sure, z is a function of x and y, but x and y are now functions of t. Compositions. Well, here's I'm going to not worry about the rigor here, this being Math 212. I'm going to just divide by dt. Take that, divide by dt. And that equation becomes just this. And notice what I have then. It's really convenient how this worked out. Looking at this composition of functions, I have a formula that relates. Let me just do it like this. I'll do it like that. The derivative of the composition to the derivatives of the input, the derivatives of what you might call the first function, right? And the derivatives of the second function. That's a nice little outcome. Everybody on board with that? All I did is divide by dt. This is a multivariable chain rule. This is a version. This is our sort of first version of the multivariable chain rule. It relates the derivative of a composition to the derivative of the individual functions that make up that composition, just like in single derivative calculus. Okay, now I would like to give you a different point of view on this formula, this chain rule formula, to think about, how does this relate to the idea of changes? Remember, we're talking about derivatives relate input changes and output changes. How does this make sense in the concept, in the context of input changes and output changes? All of these different derivatives we have written down, they all have, they're derivatives of functions that have different input spaces and output spaces. So how do all these different changes relate? And I think a good first point of view on that is to think about how changes propagate, propagation of changes. So let's look at t here. And imagine I were to change t a little bit. What do you suppose would happen if I took that value of t? By the way, before we change it, note, give me a value of t that gives values of x and y, because x and y are functions of t. And then once I have values of x and y, that between them, that gives me a value of z. So when I say I start with a value of t, that means I have values for t, x and y, and z. So that having been set, now let's change t a little bit. What happens? Okay. Well, here's one thing that happens. And momentarily I'm going to ignore all of this. We'll come back to that in a moment. One thing that happens is if you change t, look, x is a function of t. You change t a little bit, you're going to change x a little bit. Now you wiggle the input, that's going to wiggle the output. Okay? In fact, we know exactly what the factor is. The factor that you multiply by the change in t to get the change in x, that factor is dx dt. Okay. Now, what happens given that x changes a little bit? What's going to happen from that? Well, if you change x a little bit, z is a function of, among other things, x. So if you change x a little bit, that's going to cause a change in z. So you see what I mean by the change propagating. So you make one change here, that change causes this change causes that other change. Right? Okay, so when you change x, there's a corresponding change in z. Again, there's a factor that relates those changes, and that factor is that partial derivative. So now I ask you, what happens if you take some number, some change, I change t by some amount, if I first multiply it by a factor to get this change, and then I multiply by another factor. If you multiply by one factor and then multiply by another factor, altogether you have multiplied by the product of those two factors. And you can see that right here in colors, right here in this first term there. That product of derivatives is the product of these two factors that tells you altogether then how changes in t propagate along this path, that propagate through x to cause changes in z. Okay. Now you can make a totally analogous argument to point out that, hey, listen, this doesn't happen in a vacuum. You change t, yeah, it's going to change x, and this conversation's all well and good, but when you change t, that also changes y. Right? It's important. It does. It changes y as well. So let's see here. dy dt is the factor between dt and dy. And then likewise, dz dy, partial of z with respect to y, is the factor that relates a change in y to the contributed change to z. Right, so what we have here then is two different paths by which changes propagate. You can make a case for how, look, when you change t, yeah, there's going to be a propagation of changes along this path. That gives you that term. There is also going to be a propagation of other changes along a different path. Both of these paths contribute to the total change in Z. So the total of these is the actual change. So anyway, this is just intuition, but it's really, really useful intuition. In some contexts, this is far more useful. This propagation of changes point of view on partial derivatives is really kind of more useful than the derivation that I just showed you. So I think this is a great point of view, and I encourage you to think about things in this way. We will pick up here next time. No, we won't. No. Today's Monday. We have a test on Wednesday. So don't forget. So test on Wednesday. We will pick up here on Friday. Okay. See y'all later.